Hello everybody, I'm here to present our work, Learning to Singulate Layers of Cloth Using Tactile Feedback by Sashank, Thomas and Daniel, who are joint authors, followed by Zenep, Oliver and David, all affiliated with Carnegie Mellon University. Our problem statement is simple. Given a stack of cloth, we want to grasp n layers of cloth. For example, this is grasping 0 cloth layers. This is grasping 1 cloth layer. This is grasping 2 cloth layers, 3 cloth layers, and so on. The motivation for our problem is that this is a common failure case when trying to fold cloth. As seen in the GIF here, the robot needs to grasp 2 layers of cloth in order to fold it correctly. However, it only grasps 1 layer of cloth, causing an incorrect fold. Related work generally uses vision-based methods. For example, in this work, the corners of the cloth are segmented and then a push grasp is performed in order to grasp the topmost layer of cloth. Here, the edges and the corners of the cloth are segmented and a sliding grasp is performed in order to grasp 1 layer of cloth. In contrast to these works, we explore the use of tactile data for this task. One of the reasons this problem is so hard is that off-the-shelf depth sensors do not have enough resolution to detect the different cloth layers or estimate the gripper height. For example, to the left here we see an RGB image. To the right we see a depth image where we cannot make out the outlines of the different cloths. If our estimation is off by a few millimeters, then the grasp fails. As shown over here, it fails to grasp 1 layer of cloth. Similarly here, it fails to grasp 2 layers of cloth. Our proposed approach is to first collect a large amount of training data from a tactile sensor, use a classifier to train that data, and use the classifier in a closed loop algorithm to grasp the desired number of layers of cloth. Now I will discuss how we collect our training data. We use the reskin sensor in order to collect tactile training data. The reskin sensor consists of a magnetic skin that deforms when forces are applied to it. This causes changes in the magnetic flux, which are picked up by the 5 magnetometers present on a circuit board attached to the skin. Here is an example of the magnetic flux readings when trying to grasp 2 layers of cloth. Tactile feedback can vary quite a bit depending on the number of cloth layers. Here is the magnetic flux for 1 magnetometer along one axis when grasping 0 layers of cloth. Here is the same flux when grasping 1 layer of cloth. And here is the flux when grasping 2 layers of cloth. As you can see, they are pretty varied and can be distinguished. How do we label our data? The idea is simple. We put a predetermined number of gripper layers in between the arms of the gripper and then perform a large number of random grasps. Since we already know the number of layers, we can easily label the data. Here it is performing a large number of random grasps with 0 layers of cloth. Here it's doing the same with 1 layer of cloth. Here it's doing the same with 2 layers of cloth. Like this, we collect almost 2 million semi-automatically labeled data points. Now I will discuss what classifier we train. We train a k nearest neighbor classifier. It takes a 15-dimensional magnetometer input, which is the magnetic flux for 5 magnetometers along 3 axes at every time step, and it outputs the number of cloth layers in between the fingers of the gripper, 0, 1 or 2 respectively. Now we can discuss what our algorithm is to use the classifier to grasp the desired number of layers. Our algorithm is quite simple. First, we perform a grasp. Then we query the classifier for number of layers in between the gripper. If it is greater than the number of desired layers, we move the gripper up and again perform a grasp. If it is lesser, we move the gripper down and again perform a grasp. If it is equal to the number of desired layers, we directly lift the cloth and our program terminates. We evaluate our algorithm on 3 sets. One is the gray towel, on which we collect the large data set. Then the white towel and the patterned cloth, which our classifier has never seen before, and thus it shows the generalization capabilities of our method. We compare against a vision-only baseline that takes input images as shown here, sends it through a ResNet-18 network pre-trained on ImageNet and fine-tuned on the current data set, and outputs the number of layers of cloth in between the gripper fingers, 0, 1 or 2 respectively. Let us discuss the success rate for different methods. First is the fixed height method, where we hardcode a predefined height and we move the gripper to that height to perform a grasp. It gets around 60% success on the gray cloths, but it does not succeed at all on the white or patterned cloth since the thicknesses of these cloth vary. Then we talk about the image baseline. The image baseline gets an 80% success on the gray cloth, but it does not generalize to new cloths that it did not see in its data set, getting only 20% success on white cloth and no success on the patterned cloth. Finally, our proposed method, the tactile baseline, it gets a 100% success rate on the training set, the gray cloth, and it generalizes well with a 80% and 75% success rate for white and patterned cloth respectively. We have similar results for 2 layers of cloth. The fixed height only performs well for gray cloth. The image-based classifier also only performs well for gray cloth and fails to generalize to white or patterned cloth, while the tactile-based method generalizes pretty well to white and patterned cloth with an accuracy of 40% and 10% respectively. Here are some videos of our final results. Here it is grasping 1 layer of cloth. Here it is grasping 2 layers of cloth. Our final takeaways from this work is that tactile sensing is useful for grasping the desired number of layers, as we can see in this video, and it is useful for generalizing to out of distribution cloth. This work was funded by LG, NSF, and done in the RPAD lab in the Robotics Institute CMU. If you have any questions, feel free to mail me. Thank you. Thank you for watching.